So when we last left our hero, we were working on math, but I'm looking for the word characteristics of functions.
And their properties.
And their properties. Nicely done. Well played, sir. And we had already talked about domain and range, correct? Okay. And you will recall that domain is the x values that you can use, and the range is the y values. When you're searching for domain, there's two main things you have to be concerned about. One of them is
they can't be divided by 0.
Okay, you can't divide by 0, and you can't square root a negative number. Okay, good. And then we didn't really talk much about range. Range is a little bit trickier because there's no sort of easy way to do some algebra and figure it out. So a lot of times to find the range, you just look at the graph and see what y values are possible, and a lot of times we just don't care about range much at all. Okay. All right. So that gets us up to speed. So our next concept that we're going to talk about is continuity, which is a word that you use just like in normal English, not necessarily in math. So you should sort of have a sense of what this means already. So a function that is continuous is one that you can start on one side and go to the other side, and there's no breaks or holes or weird things going on. Okay, so that part should be relatively straightforward unless you are an English language learner, like from Spain or Italy, right? Across the Mediterranean from each other. Yeah, been to Spain, never to Italy. Anyway, what we're more concerned about are the different types of discontinuities when the graph is not continuous that can come up, okay? And so this first picture right here on the left is an illustration of a continuous graph. And the way I think about a graph being continuous is sort of like I said, if this is a path, or this is a mountain or something, I can start here on my little hike, and I can walk all the way from here to here without having to build a bridge or falling in a hole or anything weird like that. Okay, so that is continuous, all right? Okay, then some things that can happen, some things can happen to make a function discontinuous. And so here is an example of a discontinuity where there is just randomly a hole in the middle of the graph. Okay, so you're walking along the trail, and then you get to this point right here, and there's a hole. Okay, so that means that the function is discontinuous. The weird thing about this right here is that that hole that's missing is only just the size of a point, which is how big? Infinitesimally small, right? So you wouldn't even notice on your hike that hole was there. But so that we can sort of see and emphasize a little bit, when you see these in the textbook, they're going to just go for it and make a big old hole there, just like they make this be a point, even though that point is infinitesimally small. So this is called a removable discontinuity, because if you were going for a hike along the trail and all of a sudden there was this hole in the middle of the trail, you could get a little group of trail workers out there, and they could fill that hole, right? So you could remove that discontinuity. You could go back to the ranger station and say, hey, I noticed like a mile in, there's just this random hole that goes down through the earth and on forever. You might want to fill that up with something. And they would do that, okay? So this is a removable discontinuity. Notice in this case here is the point that we would use to fill that hole. In this case, we don't have that point out there, but it is still removable if we wanted to, all right? So that's one kind of discontinuity. Another kind of discontinuity is called a jump discontinuity. And so that, I mean, it's all just sort of English. So same sort of situation, we're hiking along this trail right here, and then again, there's a break in the trail, so we know that it is discontinuous. This time, however, the trail's right here, and then it starts again up there. So to get from this part of the trail to that part of the trail, we'd have to jump up to get to the next piece. Okay? This one is not removable. You might be tempted to think, well, you could just come out here and you could just put something in there right there that connects the trail, but what's the problem mathematically with doing that?
It'd be like teleportation.
Mathematically, what's the problem with doing that? Thanks. What is true about this, this, and this, which is no longer true about this when I make that little bridge?
Straight up and down.
It's straight up and down, which causes us a problem because
Not a function.
then it would no longer be a function. I would fail the vertical line test, okay? So this one right here is okay because this point is directly above this hole. So as I do the vertical line test, as I pass the vertical line test across this here, a vertical line across there, it only touches that one point. But if I try and build something there, then I'm no longer a function, so I'm SOL, okay? So this is a shoot. I'm out of luck.
That's not what I was thinking.
Oh, that's,
It's part of that.
yeah, shoot.
You've never heard that?
Okay, and then this one is the worst of all, because this sort of discontinuity is an infinite discontinuity, and these things would be going forever this way. And so you're hiking on a trail and you're like, wow, we've been going for a really long time and we're not really getting anywhere anymore. That's because the other part of the trail is infinitely far in the other direction above you, and so it's never going to work, okay? So, continuous, removable discontinuity, jump discontinuity, infinite discontinuity. Questions? Sir?
What's the difference between the second and third?
Nothing. In this case, we have sort of removed the discontinuity because now every value of x has a value of y that goes with it. In this case, we have not yet removed the discontinuity, but we could if we wanted to. Okay? Yes?
Would that fail the vertical line test, the infinite?
Not at this point right here, no, because what is this right here? What's the fancy word for that?
Asymptote.
Yeah, this is a vertical asymptote, okay? So those two pieces of the graph never actually get right up above each other. They get closer and closer to that, but they never actually do, okay? Great questions. Other ones? Connor?
Yeah, he does. He's just too shy to ask it.
Okay. All right, so that's what we just yacked about.
Oh, it can't be that long.
Okay, so let's look at some examples and let's identify some points of discontinuity. So this guy right here, figure 1.16 is the graph of f of x equals x plus 3 over x minus 2. Is that function continuous at x equals 2? Is the question.
How do you know?
No, because if I draw a vertical line at x equals 2, it doesn't touch either part of the graph. There's no value of y that I get when I plug in x equals 2. Okay? What kind of a discontinuity is this?
Infinite.
This is an infinite discontinuity. Since it is an infinite discontinuity, is it removable or non-removable? Okay.
Wait,
So
how do you
this
know
is an infinite, non-removable discontinuity. The way you know that is that the infinite and jump discontinuities are non-removable. You can't fix them. Okay? All right, how about figure 1.17? If I once again draw a vertical line at x equals 2, do I get a y value at that point?
Yeah, 2.
Yes, 0. X equals 2, y equals 0.
Oh, yeah.
Okay, so is this graph discontinuous at x equals 2? No, this one is continuous, okay? And once you say that the graph is continuous, then we don't have to worry about this removable or non-removable issue because it's continuous, there's nothing to remove or non-remove. Okay, so then we're just done. Okay, how about x squared minus 4 over x minus 2?
Removable discontinuity.
There's a removable discontinuity at x equals 2, because once again, if I go over to x equals 2 and then I go up to the graph to try to find out what it equals, what do you really want it to equal?
4.
You want it to equal 4, and if you decided that it could equal 4, that's how you would remove that discontinuity. But the way that it's written right now, there is no value right there, so technically this is a removable discontinuity. Let's graph this on our fancy new,
The numbers in the brackets, in the mean.
Oh, these numbers right here? They're giving you the dimensions of the graphing window. So this is from negative 9.4 to 9.4 in the x direction, and from negative 6 to 6 in the y direction.
That's what it showed up.
Okay, yeah, that's what it shows. Okay, Joseph? Yes?
So, we were all wondering at this table if infinitesimally, or whatever the word you said, is that a real word?
Yeah.
It is?
Yeah. It's a calculus word.
Let's keep graphing.
Infinitesimals.
Pre-calculus, so we shouldn't be.
Oh, okay. So we'll just go with infinitely small. Yeah. Okay. Sorry, I didn't mean to use language that you didn't understand.
Yeah.
No, what? Oh my God. Hang on.
All right, I don't know what the new graphing calculator does with this, but let's go ahead and take a look. So let's graph x squared, was it x squared minus 4? Divided by, what was it? X minus 2? Yeah?
Yeah.
So divided by x minus 2. Let's see if it shows us that discontinuity. Okay, so it does not. And so that's the problem with these removable discontinuities, is that you can't see them on the graph because the calculator is trained to just plug in numbers and then just connect the dots, and so it just makes it automatically into a continuous graph. So one way that you can tell if a discontinuity is removable or not is if you can't see it on your graph, then that's because the calculator removed it for you. Okay, so kind of weird, but maybe that makes sense. I don't know. All right, questions about continuity, big concepts. We'll talk about that a lot in calculus next year.
Good thing I ain't gonna be here.
Good thing you ain't. We good? All right, next idea is increasing, decreasing, and constant. And really the only thing that you need to know about this to make sure that you're understanding it correctly is that in this country, we start on the left and read to the right. Yeah? And then the same is true with our graph. So when we're talking about increasing and decreasing, we're always going from left to right, okay? And so it's a pretty straightforward idea. This graph right here, if I start on the left, again, I'm going to go with the hiking analogy, and I go to the right, I am going uphill, albeit gradually sometimes, but I'm going uphill the entire time. So this is a graph that is increasing over its entire domain, or from negative infinity to infinity. This one right here, again, always going from the left to the right. If I start here and then move to the right, I am going downhill the whole time. So this is an example of a graph which is decreasing. Okay? All right, Joseph's favorite kind of heights. This is where the graph is. No, those are super boring. Constant, okay? Not going up or down. And then, of course, we can mix things up and have the graph be doing all of those things, all three at the same time. So this graph is decreasing from negative infinity to negative 2. Notice when we're talking about these intervals, we're talking about the x values. Okay? So the x values from negative infinity to negative 2, the y values are going down over that interval. And then from negative 2 to 2, the y values are staying the same. And then from the x values 2 to infinity, the y values are going up. So we're going decreasing, constant, and then increasing. And then I think did I talk to you guys already about this notation? Did we talk about that last week? why some of these have square brackets and some of them have, okay. All right, questions about that? Increasing and decreasing? Pretty simple idea, pretty intuitive. Okay, so now it's your time. So this will be on a piece of paper that you are going to eventually turn in with your homework assignment on it. Will you, with your table group, and Evan and Sam, you guys might want to unite forces. Will you work your way through exploration number one? Okay. What you are looking for there is, what did you notice about the function that's increasing?
Positive.
The change in y, the change in x is positive. What did you notice about the function that was decreasing? It was negative. And how about for a constant function? All zero. Where have you seen change in y over change in x before? What did you say? Yeah, that's, we talked about slope, right?
Oh.
Delta y over delta x, like when you were in Miss Parkins' class, that's how we talked about slope and pre-algebra, I mean. Also, you can think of that, the fancy way to talk about that is rate of change, okay?
So now do we write these notes on this?
So if you want to, no, I don't want to write those notes, okay? Okay, so let's get a little bit fancier. Let's look at some more complex functions and tell whether it's increasing or decreasing, or of course it can do both. And if it's doing both, what intervals is it doing those crazy things on? So I guess we're going to look at the graph. I mean, you guys know what this graph looks like already, right? X plus 2 quantity squared. You know?
Is our notes or on our paper?
We're back into your notes.
Oh, good.
So let's go to the graph. Let's look at x plus 2 squared. A little graph practice here. So x plus 2, yeah, I can hear Joseph back there describing it correctly. It's squared, so you should have suspected that a parabola was involved. And then the plus 2 inside the parentheses means the graph has been moved to the left. Yeah, remember inside parentheses is right and left, and it's opposite of the direction that you would think it would be. So positive goes to the left, negative goes to the right. Okay, so now that we have this graph, where is it decreasing from?
Infinity, negative infinity.
Negative infinity to
Negative
negative 2.
Yep.
Decreasing, yeah. Good. You got, yeah.
I'm beating Joseph.
Yeah, right. You're beating Joseph right now, so you are definitely winning. Okay, so we're going to go we're going to go decreasing. Yeah, I'm recording for some reason. I don't really know why. I'm just going to do that every day.
No, don't do it. I don't like to do that.
Okay, so it's decreasing from
Negative infinity.
negative infinity to negative 2. And this book does something that I'm a little bit uncomfortable with. It is then increasing from where?
Negative 2.
Negative 2 to infinity. And so the notation that they use is they go with square brackets on the negative 2 both times, okay? Which I don't like very much because that means that it is both increasing and decreasing at negative 2. Negative 2 is included in both of those answers. And that makes me a little bit uncomfortable because it doesn't really make sense that it should be doing both at the same time, right? But I think the idea for them is that it can't be neither, so they just like throw it in there for both, all right? Okay, questions about that? All right, let's take a look at another one. X squared over x squared minus 1. So, I don't know why that keeps happening. X squared divided by, what was it? X squared minus 1?
Yep. Whoa.
Okay, yeah, whoa. So this is a rational function. So remember this last year, this is Samantha's favorite chapter. She only retook that test quiz like, 4 times or something, but got it in the end. So a lot of weird stuff going on here. This function is, which do you want to do first, increasing or decreasing?
Decreasing.
Decreasing? Okay, so this function, if I'm moving this direction, this is all increasing. This is still increasing, right? So it starts decreasing at 0. And then you would like to say that it is decreasing from 0 to infinity. But what do we have right here?
An asymptote.
We have an asymptote. We have a infinite discontinuity, so I have to indicate that in my answer. Where is that discontinuity? At what x value? 1, good. Because if I plug 1 in here for x, 1 squared is 1, 1 minus 1 is 0, and we can't do that. So this is weird, but to write down the decreasing for this one, or no, did we do, yeah, we're doing decreasing. Okay, so to write down decreasing, I have to say it is decreasing from 0 to 1, and then from 1 to infinity. Okay, so this time I'm using round brackets around the 1 because 1 is not in the domain of the function, so I can't actually include that in my answer. Okay, and again, it would be a lot easier to just say from 0 to infinity, but unfortunately it would be mathematically incorrect. Okay. All right, and then looking at that graph again, or remembering it, or looking at the answer that I already have, that means it's going to be increasing from, let's go back to the graph, Vern. That's increasing from
Infinity.
negative infinity to negative 1, right? And then from negative 1 to 0. No, it stops increasing right here. Okay? So it's kind of the opposite of the other one. So it's increasing from negative infinity to negative 1, and then from negative 1 to 0. Okay? Questions? Okay, can you see a little bit how the ideas of continuity and increasing, decreasing sort of connect a little bit because there's a discontinuity in here and that affected our answer and so forth? Okay. Oh, okay, you may have noticed that we were making some assumptions about the graphs. How do we know that they don't turn around somewhere off the screen? So in other words, when we say that this graph right here is decreasing till infinity, we're assuming that at some point it doesn't just start going up again. And you might reasonably ask, how do you know that? How can you tell? And apparently we're going to address that later in the course, okay? But the best way to do that is through the use of calculus, which we'll learn next year. Okay? All right, that feels like enough for me today. You guys ready to work on some problems on your own? Okay, so take advantage of the time, 20 minutes. Get as much of this done as you can in class.